You're probably wondering why there's a picture of an old town behind me when you came to this video expecting to hear about path functions and state functions. Well, there's a lot of similarities. And state functions or variables describe what's going on in the system itself. Like in state 1, there's internal energy, pressure, volume, temperature, and the same thing with state 2. They are both describing what's going on in the system or in the town. Whereas our path functions, notably heat and work, describe the amount of energy that's being transferred between states as the system gains or loses energy. And that's pretty much it for the video. You can click off now. No, we'll formalize this a little bit more. And let's say we have some system at a given state, and we'll say it has 100 joules of internal energy, and it's at 25 degrees Celsius, and then we heat it up so that it is at 30 degrees Celsius and say 200 joules of internal energy. Now there's two ways to add energy to the system. We can do it via heat, or we can do it via work, say cover it up and shake it. That's a form of work. The key thing is that heat and work are path functions, and their values describe the amount of energy that's being transferred between states. So that's the key part. Heat and work describe how energy is being transferred. If we imagine heat and work as this person with the wheelbarrow, and let's imagine energy as this fire. Now, fire is more like heat, but just bear with me because it's hard to get a picture of actual energy. Let's say we have some energy pile, and we're trying to get energy from this pile into the system. Well, heat and work describes how that energy is being transferred. Heat and work doesn't carry the energy as I have in this wheelbarrow. It just describes how that energy itself is transferred. So a little amount of energy being transferred can be thought of as in an infinitesimal form. So if we pick on heat, dq represents a small amount of energy being transferred as heat. And the total energy that's transferred as heat throughout the whole process is the sum of all the infinitesimal portions of heat throughout the process. Now, these are infinitesimally small, so really to add them all up, we need to add an infinite number of ones. So we need to add a limit as the number of dq's goes to infinity. And this limit definition, really we can turn this into an integral, where q, the energy transferred as heat, is equal to the integral of dq from the initial to the final state. Now, there's a difference here. This q, even though it's an integral of dq, it doesn't equal the change in q. So like your normal integral from Calc 2, this would be delta q is the integral from q2 minus q1. That's not the case here. Q is not equal to final minus initial. And your prof or textbook might write dq with a line through it, the d cross like this, just indicating that it's an improper integral. So q, really, you can express it as an integral as a path function from the initial to the final state of dq, but its value depends on the path. So as we go from our initial to our final state, we can add 100 joules via heat, or we could add it another way. Maybe we'll add 50 joules of energy as heat and another 50 joules of energy as work. The value of heat and work depend on how we went from the initial to the final state. However, for a state function like internal energy, it doesn't matter how we got to the final state. The change in internal energy is always the same. It's going to be equal to the integral of du from initial to final. And just like in normal Calc 2, this becomes internal energy final minus initial, or delta U, which is 100 joules regardless of the path. And that's the key difference between state functions and path functions. They're actually completely different. State functions describe the state of the system, what its internal energy is, pressure, volume, temperature. It can also have enthalpy and entropy. So the value of these depends on the actual state. We're not transferring energy. The path functions tell us how much energy is being transferred between states. It's how much energy we're transferring as heat, or how much energy we're transferring as work to get there. So their value depends on how the energy is transferred. Okay, so for a state function, I'm picking on internal energy. The integral of du from initial to final state is delta u. And in this way, du represents an exact differential. It's a differential that you're normally used to seeing in Calc 2 and integral calculus. Now, there's another definition of exact differential that your prof probably went into, and I have a video on. You can check that out. But for us, this equation will suffice for that definition. So delta U is, in its truest sense, final minus initial. And U itself is a state function, just like H, enthalpy, is a state function. But for our path functions, the integral is not equal to delta Q. These dq's and dw's are called inexact differentials, and we may write it with the bar or this little delta, or this delta might have a bar as well, indicating it's not a true differential. We can't integrate and get the change. So don't use this delta Q, just kind of ignore it exists. In some circumstances, delta Q is appropriate, but for the vast majority of times, just like ignore this, don't use it, because there's no initial heat or final heat. There's only heat during the process. Ooh. Great. Now for a cycle in which the final state is equal to the initial state, the change in any state function is going to be 0. But for a path function, it may not be 0. It depends on how we did the cycle. That's how its value is derived. You can think of the Carnot cycle has heat and work, but it's not 0 during the cycle. Say we have some state 1, and we go through a bunch of states, but then end up back at the same initial state in which we started. Well, the change in a state function, again, I'm picking on internal energy, delta U is going to equal to the integral throughout the cycle, and this circle just means we're finishing where we started. The final state is the same as the initial state, so the integral of du. This is equal to delta U, so U1 minus U1, and that's got to be 0. And this is true for any state function. So the integral of enthalpy, dH, dg, dp, or any kind of state function you can think of. Right. So to summarize, state function versus path function, the state function derives the value from the state of the system as it is, but the path function describes how the energy is transferred. The differential of a state function, dx, describes an infinitesimal change in state, and it's also an exact differential. But for a path function, the dq or dw, that represents an infinitesimal amount of energy added or removed, and it's an inexact differential. So for the integral, the change in the state function is equal to the integral of dx, whatever the state function is, from the initial to final state, which is truly final minus initial. But for a path function, the integral depends on the path. We can't write it out. So q is equal to the integral of dq. There's no delta q. All right, hope that was helpful. Understanding these basic concepts of thermodynamics is crucial in doing very well and not being like me when I went through it for the first time, totally confused and not know what's going on. Understanding these core concepts will help you through the rest of the term, the rest of the course, and in future years as well. All right, hang in there. You can survive. Cheers.